Hello and welcome to my display in Minecraft. This is a display that I've been working on for about 2 weeks. It normally has a white canvas, but you can have up to 7 colors, and this is including black and white with 5 extra colors, and has a resolution of 8 by 8 blocks. This screen is controlled by a 32-bit Redstone parallel interface. For now, I've just got a little bit of program memory so that you can put images in, but normally this is intended to be connected to a Redstone computer so that as the computer operates, it can draw pixels and use it as a graphics processor. So the way this computer works is it uses the concept of falling concrete powder. So I have here a demonstration where I have 3 pistons and some concrete powder, and I have the white canvas. So what would happen is for any given pixel, I would extend the bottom 2 pistons, and then I would deposit whatever color I want. And in this case, it's red. And as it's a gravity block, it falls down. And then I would push the piston directly above it and retract both the 2 pistons there. And that would replace the pixel. Instead of being white, it would now be whatever color you dropped in. The fallen block simply drops and lands on the redstone and turns into a block. And if you can see down here, there's a little bit of redstone, and back here is the piston array. All of the wires are connected through these interface wires, and this is the logic side of things, which then is attached into the program memory. So what I'm going to do is I'm going to start a demo that I've created. This demo is just a smiley face, and so that button there just starts the program memory. So what's going to happen, it does create quite a bit of lag. So here I have an image of the end result. This is the way it's programmed. It does it by a row and pixel mode. So there are 2 different modes. Pixel mode is where you can choose individual pixels on any given row or any given column or in a region, and any of the overlapping areas will be that specific color that you have used. So the second mode is a row by row mode. So the first line of program memory here, we have selected row mode. Now I've created row mode because it's a much more efficient way to draw pixels. So we've got here this top area, which is entirely yellow. So what I've done is this is the layout of the grid. It starts from the bottom, goes up, and then starts from one end and goes to the other. So in this case, I want the 8th row to be entirely yellow. So I put a torch on this 8th row here in the orange section. And then the first entry here is what column I want that area to be. So in this case, I've just used the binary value. It's a 3-bit color for yellow. So then whenever the program encounters this row, it will color yellow. The second mode is the pixel mode. The pixel mode looks for the intersecting rows and columns and colors accordingly. So in this case, we've selected rows 6 and 7, which are these 2. Then the placement of the color values is what determines which columns. So in this case, we want columns B, C, and F, G. In order to make these red eyes, we want columns B, C, F, G that are intersecting with 7 and 6. So we just select 7 and 6, and then where we have B, C, F, G, we just put the color value. So in this case, red is 0, 1, 0. And same for F and G. If it doesn't have a color, then you just leave it blank. It sort of represents 0, 0, 0. If you want to use black, then the code is 0, 0, 1. And if you want to use white, it's 1, 1, 1. Normally, you can assume the canvas is just blank. And when the canvas is blank, it will be whatever previous block is there. It will just be skipped. The next step is we want these two blocks here. So those two blocks are on row 4, but intersecting with B and G. So we select row 4, and it's intersecting with B and G. And so we color those black and black accordingly. And so for this row down here, again, row 3, we have selected row 3, and we have colored B, C, D, E, F, and G because it's intersecting with B, C, D, E, F, G. And lastly, the same is for the last program memory, and we can see that the program has actually finished on the left. So the benefit of doing it this way is that pixel mode skips unchanged pixels. So if we saw when it was doing row 4, these 4 pixels here are completely unchanged. And so as a result, all it does is it draws G and then skips over and draws B. It does not go white, black, white, 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 black, black, white. All it does is just go black, skip, black, because that's what we've told it to do, black, and then those are skipped, and then black again. That's the benefit, is that if we were to draw it completely manually, it would use up a lot more time. We saw this image only took a couple minutes to draw. If we were to enter it all manually, it would take far longer, and we'll talk about that a little bit later. And so one of the benefits of this design is that we can actually change any pixel on any row. So for example, this example here, where we've got a rainbow colors, where you have black, red, orange, yellow, green, blue, white, black, all I've done in this example is I've selected all of the rows from 1 to 8, and then for each of the columns, I have just entered a different color. So in this case, it would be black, red, etc. And because I've selected all the rows, it will manually go through and it will do it for all of those rows in the single command. So this entire picture here only took one command to do. And that is why this interface is so powerful, is because you're looking at the selection between rows and columns, and that's where the data is encoded. So you can do entire blocks of color, say from B to F, intersecting with 7 to 3, and you can do that one color. Or you could do columns, one color, or you could do rows. And if you are doing rows, I've allowed for you to use the row mode so that you can do it faster. Here is another example where we have the Australian flag, the country that I live in. And in this example, I've actually broken up the steps of how I would create a picture. So I'd have an idea of what I'd make, and I'd have to try to optimize the way that the GPU, if you can call it a GPU, draws the image so that it uses the least amount of commands as possible, and therefore the least amount of pixel draws and takes the least amount of time. So in this example, we're using row mode to fill in the entire background as blue. And so all that's done by is selecting rows 1 to 8, and we're choosing the columns A, B, C, D, E, F, G, H all to be blue. And so it just goes through one at a time, and in row mode, which is designated by that, we go through and make the whole background blue. The next step is to fill in this area here, which is a 2x3 area of red. So we select the rows 7 and 6 here, and then we select the columns A, B, C. And so that allows ABC to intersect with 7 and 6, and we've designated the colors red, red, red. So accordingly, it's red. The next step is the 2 white dots here. And so we've selected row 4, and we want E and G to be white. So row 4, we have a torch, and we have E and G both designated as white. We have these 4 corners here, and that's done by selecting rows 8 and 5. And those rows are then filled in with intersecting A and C as white. The next step is by using, I designed this image so that it's more efficiently drawn with the Southern Cross. So we want to fill in this block here white, and this block here white, and we want to put the star here, but we're actually going to redraw this pixel here so that it's easier to render. So that's where we get these four. It's actually, so this block here will actually be drawn twice. However, it's more efficient to do that because it's easier to draw. So that's done by selecting the rows 2 and 5 and having intersecting C and F. So we have 2 and 5, and we also have intersecting C and F, and that is of color white. The last step is to have the two red dots of the Union Jack. So that's just done by selecting rows 8 and 5, as we have done here. And then just for column B, we just want red. So anything in that column will be red. So as the pixel mode doesn't have anything in the row, that's how you designate whether it's pixel mode or row mode. So this Australian flag took about 4 minutes and 10 seconds to draw. Per pixel, it's about 6 seconds when in pixel mode. So going from that to 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 that would take about 6 seconds per pixel. So if you've got 8 of them, you can imagine it would take about 50 seconds per row. So that's why row mode is so useful, because when in row mode, it only takes about 8 seconds per row. So if you were to do the entire image manually, just by using literally each individual color value, here I've designated each color value, so you will be doing it pixel by pixel and then row by row. You can actually see the flag is sort of represented here in the data. This would take an enormous amount of time because you're doing everything manually. So rather than using row mode to draw the blue, you're doing it individually. That's why it takes so long, and that's why row mode is so useful. Some of the major hurdles when creating this was that the timing of the pixels was quite difficult. So for example, here I've got the pixel array. As you can see, I've got an example up there, but having the pistons come out in timing with the falling concrete powder was very, very difficult because you only have a small window, and being able to synchronize it for all 8 rows was very difficult. So this section up here is what selects the color. You have the 8 bits of color here, the 3 bits, and the 8 different colors are then calculated through this binary to decimal decoder. It then goes to the designated color and dispenses it down to the piston array. Some of the ways that I allowed for the timing of the pistons is I actually used my phone with slow motion mode, and I just stood up here and watched over and made sure that all the pistons were synchronized. Another major hurdle was that, as you can imagine, all of those piston wires condensed. Actually getting it out expanded was very, very difficult. And so having this monstrosity to then lead back to the whichever column, whichever row you select was very difficult. So for example, in this case, you would select the row by applying signal to the pink wires, and these are some piston AND gates. And so you've got 2 torches on a block, and then you've got a torch in the middle, and the torch in the middle turns on and the piston comes out. So once this block and that block have got signal, the piston comes out for that individual pixel. So this is row per row, and the signal just comes out and splits across all the different columns. And then for each individual column, you have a wire coming in, and that's spanned across all the rows using this glowstone monstrosity. And that's some testing I used to try to synchronize. Here I was trying to design, this is some of the early phases of my planning, and I've been trying to design, for example here, determining the colors where 000 is just unchanged, trying to figure out how exactly do I take it from a grid onto the ground. And so one of the issues I had was that I wanted to try to, whenever you sent a pixel value, I needed it to then signal the piston above it to actually push the block out. So if you remember to our demo before, we had a piston go out that acted as a landing platform, and then you actually have the piston above that's the one that does the pushing. So my idea was that I could try to extend it to have it go out like that. And so this is, as the signal comes in, you could have a repeater, which then goes to the line above. But my issue is then it would propagate up to the next row and the next row and the next row. So if I signal to the middle, it would then signal all above. So I had to try to design a way to have the pistons extend in such a way that it can't be reversed. And that was done by having this diagonal. And so the way I actually implemented that in the end was not using repeaters directly, but by having the pistons signals would come through here, it would turn on a torch, the torch would then turn on a torch on top while also outputting forward. The torch outputting forward would then hop up a block of glowstone and continue forward, but then because there's a torch here, it would start this line of 5 repeaters. These line of 5 repeaters would then jump up to the top line. And you see this block of glowstone here? This was vital because if you look here, it's actually the same block of redstone that is on the row below. So if this was a regular sandstone block, I would actually turn on this signal above, and that's not what you want. So in order to prevent that, you have to use a block of glowstone as well as a block of glowstone up here so that you can get the signal to go through the block. And that was the design I ended up on in order to uh, change the pixel going in, and then subsequently a few 2 seconds later the pixel above it. Got a smaller demonstration here. So if we recall, these are all the columns and those are all the rows. And so what I'm going to do is I'm just going to designate one torch here and then all 3. So this would be for 2 columns, and I'll have that intersecting with 2 rows. So this will just literally output wise. It doesn't actually do anything. It's just for testing. The way this actual logic side of things work is that think of it like a nested for loop. So a for loop within a for loop. So for each row, it will go through each row that has a torch selected. And if it doesn't have a torch selected, it will skip the row. And then for each row that is selected, it will go through the columns. And if there is a column that doesn't have any data, it will skip it. And it will only act on the columns and the rows that have a torch. So for example, these first 2 rows here and the second 2 columns have data, but the program will actually, on the first row, it will actually go through all 8 columns, but because these don't have any data, it will skip it. And then when it goes to the second row, it will go through these again, and then it will skip the rest. And then it actually does go through the rest, but because they don't have torches, they skip. So if I turn on, I've just got green wire here. If we look at the output, we've got that torch on the 1 column, and then we've got the torch on the 3 column. That's the second column. So these down here are the columns, and these are the rows. The rows go from right to left, and the columns go from left to right. And so as the columns went, the first time we put down the torch, it went from right to left. So because all the others were off, this was the one that turned on. And so then we go first column, second column, and then from rows we go second row, or rather last row, and then from left to right, column 1 and then column 2. And so it does actually do all of them, it just skips. And so this is how I use the row mode, is basically I have it go to the first row and the first column, and then I essentially trick the computer into thinking it's changed the row. So as it goes to the second column, it just changes to the second row, and then it just hops like that. So the advantage of skipping unused data is actually just inherited by the row mode. One of the other issues I had was when trying to pick a color, this decoder, sometimes when you change from one color to another, so for example from yellow to orange, it would have intermittent signals. So these are the output wires here. These are for the 8 different colors. the first one is unused, so it doesn't actually do anything. So these 8, so sometimes when it goes from one to the other, as the pistons move, it will activate a color that's not intended to be activated, and so you'd have duplicate colors that would sort of break the color because you'd have a color that dispensed that wasn't meant to, and then it would create an offset that sort of accumulates over time. The way I got around that was by having this check repeater stack where basically once the piston's color is chosen, this will only go down after a certain amount of time. There's a set delay, and then this will pull back up and then allow this decoder to change. So this decoder is not allowed to change while these pistons are down and let the signal through. These pistons, whenever the signal is changing, are always up, and that's how I got around the problem of having the colors mix. As I alluded to before with the Australian flag, there are sort of multiple ways to arrive at the same solution. So these two solutions here and here will get the same thing. It's just the difference is how efficient the program is and how much time it takes. So if you really wanted to do each value individually and have it draw one pixel at a time, you could do that. However, this is a more efficient way and it's a lot faster to draw it this way. So I would like to actually go through and show the process of designing a picture. So here I've got another flag. Hopefully it's a little bit more recognizable. And so we're going to go through the process of the thought process of how exactly I would make something like this. So I look at this and I think, okay, there's a lot of red and white horizontal lines. I could use row mode for that. So I guess the thing to decide is what do you want the row mode? Do you want the red stripe at the bottom or the red stripe at the top? So I'm going to go red stripe at the bottom. So that I want row 1 to be red. So I could go row 1 is to be red. And then I also want row 2, 3, and 4 to be selected. 2, 3, and 4 to be selected. So then the way the color is determined in row mode is it's simply an order of which it renders, and it renders from the bottom up, so from 1 to 8. So in this case, 1, 2, 3, 4, we want red, white, red, white. So we're going to do 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1. So that will be red, white, red, white, and that will do these bottom 4. This will be red, and then the other sections will be white. So this entire area here will be red, and this will be white. And that's done in the one command. So now we have to worry about the top section, as well as these sections here. Now, this is a little bit more difficult because of the star configuration. And there's not really any easy way to do this quickly because you've got what we want is red over here and red over here, but we also want this entire area to be blue. So if we were to do this in row mode, remember row mode does the entire row. You cannot select columns in row mode. It's entire row. So we could do this entirely blue, but then that would be a problem because if we were to select the whole thing's blue, we'd need to overlap it with the white pixels, and then we'd need to draw individual red ones here and here. If we were to do row mode, then we would then need to overlap red here, white here, white here, and that would actually take longer than if we were to do it individually. So the best thing to do is actually manually specify the pixel values, unfortunately. So in this case, the best thing to do is probably, so if we select column 5, we want to specify, so these want to be red, and we want these to be blue. If we want this entire area to be blue, then we should specify where we want the stars to be. We could have, it's a bit difficult to represent the stars without many options. I think that will have to do, because otherwise it would clash with this. So we're going to do 4 columns blue, 4 columns red. So we're going to do blue. The code for blue is 110. So 110, 110, 110, 110. So that specifies these 4 are blue, and then we want to specify the last as red. 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. So now that's specified the first 4 are blue, the second are red. Next, we want to specify blue, white, blue, blue. So for column 6, we're going to specify blue, which is 1, 1, 0. The next is white, which is 1, 1, 1. And then blue again, 1, 1, 0. And lastly, blue again, which is 1, 1, 0. And then we have white. Now, the other thing is that with this Australia flag, we assume that the canvas was not white. So that when we did the background, we just did the entire thing blue. In the row mode, I have chosen to do the white lines. However, we can assume the canvas is actually blank. And so if we only assume it's blank, then we only need to draw these red lines and these red lines. And it would be a little bit faster, but for sake of if there's something else on the canvas, we want to overwrite that, and we're going to just rewrite the white lines. So in this case, we've done the first 4 as blue, white, blue, blue. Next, we want to do the last 4 as just white. Next step is to draw this line, so line 7. We are selecting the 8th one, which we're specifying here, 7A, and we want that to be white. And then we want the next one to be blue. So we go 1, 1, 0. Next one is white. We have 1, 1, 1. And the next one is blue, which is 1, 1, 0. And then we want these 4 to be red. So red is 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. Lastly, we have this line, which is actually identical to line 6 here. And so when we're drawing line 6, we can actually just put, we want to do line 8 as well. And because these are the exact same, it will just do a duplicate. Because we've only specified line 6, once it does line 6, it will then go onto line 8 and do the exact same values. And that's it. That would be the drawing. And that's basically complete. I hope that's a little bit insightful on how to program it. When you're actually placing the torches, when you're programming it, you will see it's ordered A, B, C, D, E, F, G, H. That's because it's easier to plan. However, it is very, very important to note that when you're placing the torches, it actually A starts from the right. So here you've got A, and this is still the correct representation. So for example, if we look at the code for black, it's 001, you would still place a torch wherever you want a 1. So this is 001, and that would represent black for this column. And A starts on the right, and then as you head towards the left, that's when it goes B, C, D, E, F, G, H. However, for the rows, the order on this sheet is actually correct. Here we have 1 to 8. So here we have row 8, 7, 6, 5, 4, 3, 2, 1, 0. Well, there is no 0 row. And it's drawn from the bottom first. The way that the program counter works is by just moving a redstone block. So this sand, it's not a great solution, but this sand simply moves along and you have a redstone block, and whenever you have a new line, it simply moves the block along. The way each individual pixel moves from left to right is that we have the signal coming from the program memory coming down here, and we have this glowstone line that is always on. That is preventing these torches down here from allowing the signal to come down. So even though this torch is down here, these torches are on, which does not allow the signal to come through this bus. So if we refer to my plans earlier, we have here each individual line, 1, 2, 3, 4, 5, 6, 7, 8, and they all share a common bus. But there is a signal that is preventing it from turning on. So here we have the carry in, which is almost like the start signal, and we have two AND gates. So we have the row, which is whether or not it should turn on, and then we have the inverse of it. And so as the carry in turns on, there'll always be one that's on. And so if, for example, we want it to draw that pixel, then the row will be on and the carry in will be on as well, and then it will turn on this AND gate, which will then draw the row. However, if the row is off, this inverse would mean that this AND gate is on whenever the carry-in signal comes down. And so that would mean that instead of drawing the row, we want to just go straight to carry out and go on to the next pixel. After the row mode is drawn, if the row is true, then it will just propagate down here and go to carry out anyway after a set amount of time. As for the second area, we have the carry-in signal, which will do a similar thing, but then after the first AND gate, it will go through a latch, and the latch will essentially lock it into drawing that particular row for as much time as it takes to do all of the pixels. Once that is complete, the last carry out signal from all of the columns will then go into the reset line of the latch. It will then act the exact same as the pixels and go to the next row. And if the row is not enabled, then it will just go all the way until the final end of the program. And here we have another example. After a set amount of time, it will go down as well. So in this case, we have the signal bus for the colors, and each line for each column is correlated to go down. However, that is being prevented by this glowstone line. If we move over to the right, we have the on button, which is sort of the thing that initializes it. So as this on button turns on, it just creates a small pulse, and all the small pulse does is we have this AND gate here. If this row is enabled, which is specified by the orange line down here, if this row is enabled, then both this and this will be true, and then it will come out here, turn this torch on. It will then, we have a latch, this will latch on. When this latches on, it will then output data to, it will say, yes, okay, I want to output to row 1. This line here, the one that changes from orange to green, this goes on when all of the columns are done. And once this line goes on, it needs to change row. It's finished. So then that will come over here, and there is an AND gate. So we have the latched signal that's on, and once it receives a new change row, then this will turn on. It has a small delay. It will then carry out onto the next row. However, if this row was never selected, we have a direct inversion. Here is the input for if the row should turn on or not. If it's turned off, then this directly inverts the signal on the other side of the AND gate. And so when it initially gets that start signal, if it doesn't want to draw this row, then instead of going through all that repeater, latch, all that drawing the row, it would just simply output an on signal to the exact same place after the repeater stack. So then it will carry on to the next row. And that next row essentially acts as an on button to the next row. And then if that hasn't got its row selected, it will just go to the next one, and to the next one, and to the next one, until it encounters one that has a row that's turned on. If the row is turned on, then the latch will turn on, and then it will begin it will come over here. Once the latch turns on, it will simulate a pixel draw function, and this does a entire row. So this is a gigantic pulse limiter, which basically gives a pulse of a fixed length, and then this goes into essentially the same thing. So we have here whether or not the pixel should turn on. That's determined by literally an OR gate. So if any one of these, if I have specified a torch in any of these three places here, then this column will be designated to turn on because we have an OR gate if the first position or the second position or the third position. And because we're using glowstone, the signal can't go back down, which is very useful. This OR gate then goes into the AND gate. And so here we have the first AND gate, and here we have the input for okay, it's time to turn on. If this is off, then that will determine that the other area should be inverted. And if that should be inverted, then the output, which is determined up here because there's not enough space, will just simply say, hey, move on to the next one. And that will go into the same place that that pulse goes into. And if again, this row is not selected because there's no torches down there, it will then go on to the next one. And it will keep doing that, and it will keep skipping pixels and rows until it encounters one that's on. And only then will it actually output a signal. If the signal is on, it will output the signal to this torch. And so when it outputs the signal to the torch, it can go one of two directions. It can go two directions. It will both go to down here, which will turn on this torch, turn on that torch, which will then allow, it will turn on the redstone line, which will turn off this torch and will allow now that these three torches are no longer on, it will allow the signals, the natural signals for whatever you've selected, to go down to these lines, the giant bus bar. So if I, for example, remove that, it will turn this torch on, which allows the signal to go through these glowstone blocks and then allows these torches to turn off. And you can see the signal here propagates down below. You can see here we have two signals for the two lines that are on and the one that's off. The last thing to note is that when the signal goes on this redstone line here, which turns off these torches so that the signal can propagate downwards, it also comes up and goes onto this redstone line here, which allows the signal to carry out onto the next pixel. In addition, it also goes up and travels to signify to the display to draw that pixel. And so it's that overlap of the X coordinate and the Y coordinate which allow the specific pixel to be drawn. And then you have the mechanism of the pixel above automatically pushing up, which allows the falling concrete to land. Alright, I hope that was informative enough. I would like to make another video at some point programming a few more designs and just sort of going through the placement of the torches and showing you the different demos. I will have a world download in the description for you to have a bit of a play around with. It may not be super functional. It does, as you can see, it works with the smiley face, but there are some things that don't quite work. I will hopefully make an update and give you a correction world download so that it properly fixes it. If you do want to just program it one line at a time, you can always just place torches wherever you want along this, so the purple sections, and only do one command at a time. This blue aqua line here, that's the row command. And that is where you actually specify whether a torch or not should be on, and this green line is the turn on function. So once you have entered all of the data and whether or not you want to use row mode, you put a torch here, and that's what actually draws. And so I'm hoping to have that fully functional at some point in the future, and I should be able to update you guys when that is. Thank you for watching.